There is a number so large that your brain refuses to hold it. It slips through thought like water through open fingers. You can say it. You can write it down. You can even calculate with it. But you cannot feel it, not truly. A light year. In the United States, we measure distance in miles. We know what a mile feels like. We drive it. We walk it. We run it. We look at the road stretching ahead and instinctively understand scale. 10 miles is far. 100 miles is a trip. 3,000 miles takes you from New York to Los Angeles. That distance has weight in your imagination. But a light year is not just bigger, it is different. Light travels at 186,000 miles per second. In a single heartbeat, it circles the Earth more than 7 times. In 1 second, it could fly from New York to Los Angeles over 40 times. In 1 minute, it travels more than 10 million miles. In 1 hour, more than 600 million. In 1 year, light crosses nearly 6 trillion miles. 6 trillion. That number is not just large, it is neurologically hostile. Human intuition evolved to track footsteps across a savanna, not photons across the cosmos. Our ancestors survived by estimating the distance to a tree, the speed of a predator, the length of a day. No one needed to imagine 6 trillion miles. No brain was sculpted by natural selection to comprehend interstellar emptiness. And yet, that is the unit astronomers use as casually as we use miles. The nearest star beyond our sun lies more than 4 light years away. The Milky Way spans over 100,000 light years from edge to edge. The most distant galaxies ever observed are billions of light years away, meaning their light began its journey before Earth even existed in its present form. A light year is not just distance, it is time. When you look across light years, you look into the past. You are not seeing space as it is. You are seeing it as it was. This is where the human brain begins to fracture. Distance becomes duration. Seeing becomes archaeology. The night sky becomes a museum of vanished moments. We live on a small world orbiting a modest star in the suburbs of a galaxy that is itself drifting through a cosmic ocean. And the only reason we know any of this is because light, traveling at a finite speed, carries stories across incomprehensible gulfs of space. Tonight we confront the scale that breaks the human brain. Light years. If you are drawn to the quiet, overwhelming truths of the cosmos, subscribe to The Boring Universe. Like this video to support deep space storytelling, and leave a comment telling us which part of the country you are watching from. Now, we begin. Before we can understand a light year, we must understand light itself. Light is not merely illumination. It is the universe's ultimate speed limit. According to modern physics, nothing with mass can travel faster than light in a vacuum. This limit, approximately 299,792 kilometers per second, or about 186,000 miles per second, is not a technological barrier. It is woven into the structure of spacetime. In the late 19th century, physicists believed that light behaved like a wave moving through a medium called the luminiferous ether. This invisible substance was thought to fill space, providing something for light to ripple through, much like sound travels through air. But experiments, most famously the Michelson-Morley experiment, failed to detect any evidence of this ether. Light speed appeared constant, regardless of Earth's motion through space. This puzzling result set the stage for a revolution. In 1905, Albert Einstein published his theory of special relativity. He began with a simple yet radical postulate: the speed of light in a vacuum is the same for all observers, regardless of their motion. Whether you are standing still, moving toward a beam of light, or racing away from it, you will measure the same speed. This defied common sense. In everyday life, speeds add and subtract intuitively. If you throw a ball forward from a moving train, its speed relative to the ground is the speed of the train plus the speed of the throw. But light does not obey this logic. Its speed remains constant. To preserve this constancy, space and time themselves must adjust. Special relativity revealed that time can dilate and lengths can contract depending on relative motion. As an object approaches the speed of light, time slows down for it relative to a stationary observer. Its length along the direction of motion shrinks. These are not illusions or measurement errors. They are physical realities confirmed by countless experiments, from particle accelerators to precision clocks on satellites. The speed of light is not just fast, it is foundational. Because light speed is finite, information does not travel instantaneously. When you look at the moon, you see it as it was about 1 second ago. When you look at the sun, you see it as it was about 8 minutes ago. The sunlight warming your face left the sun before you began reading this sentence. This delay scales with distance. The nearest star system beyond our own is Alpha Centauri, located about 4.37 light-years away. That means the light entering telescopes tonight left that system more than 4 years ago. If a hypothetical civilization around Alpha Centauri observed Earth with powerful instruments, they would see our planet as it was over 4 years in the past. Light years transform astronomy into time travel. But first, let us ground this abstraction in numbers. 1 light year is the distance light travels in 1 year. Since light travels about 186,000 miles every second, we can multiply that by the number of seconds in a year. There are roughly 31.5 million seconds in a year. Multiply 186,000 by 31.5 million, and the result is about 5.88 trillion miles, nearly 6 trillion miles. For comparison, the average distance from Earth to the Sun is about 93 million miles. Astronomers call this one astronomical unit. Light takes just over 8 minutes to cross that gap. The distance to Pluto varies, but at its average it is about 3.7 billion miles from the Sun. Light takes roughly 5.5 hours to reach Pluto. These distances already stretch comprehension, yet they are minuscule compared to a single light year. If you could travel at the speed of a commercial jet, roughly 600 miles per hour, it would take you more than 1 million years to travel a single light year. Even at the speed of the fastest spacecraft humanity has ever launched, it would take tens of thousands of years to reach the nearest star. The scale is not merely large, it is alien. Our brains evolved to operate within a narrow band of spatial and temporal scales. We intuitively grasp meters and miles, seconds and years. Beyond that, our intuition collapses into symbolic manipulation. We rely on scientific notation, on exponents, on metaphors. We speak of cosmic distances in terms of time because distance alone has lost meaning. This is why astronomers prefer light years over miles when discussing interstellar space. Saying that Alpha Centauri is 25 trillion miles away communicates little. Saying it is 4.37 light years away embeds distance within the fundamental constant of the universe, the speed of light. Yet even this reframing does not rescue our intuition. The human brain struggles with exponential growth. Studies in cognitive psychology show that people systematically underestimate exponential processes. We expect linear change because our daily experiences are mostly linear. But the universe is governed by powers of 10. From atomic scales to galactic superclusters, reality expands across magnitudes that dwarf human perception. A light year sits at a tipping point where numbers stop being experienced and start being endured. Consider the structure of our galaxy. It is a barred spiral galaxy containing hundreds of billions of stars. Its diameter is roughly 100,000 light-years. That means if a beam of light left one edge of the galaxy, it would take 100,000 years to reach the other side. When you look up at the night sky from a dark location in the American Southwest or the plains of the Midwest, you may see a faint band of light stretching across the heavens. That band is the combined glow of distant stars within the Milky Way. Some of those stars are a few hundred light-years away. Others are thousands. The light entering your eyes tonight began its journey before modern civilization existed. You are not seeing the galaxy as it is now. You are seeing layers of history stacked across distance. And beyond the Milky Way lies the Andromeda galaxy, approximately 2.5 million light-years away. The light we observe from Andromeda today left that galaxy when early humans were crafting stone tools. When you see Andromeda through a telescope, you are looking 2.5 million years into the past. The deeper astronomers peer into space, the further back in time they look. The most distant galaxies observed by powerful space telescopes appear as they were billions of years ago, not long after the Big Bang. In this way, light years become a ladder descending into cosmic history. But this leads to a profound implication. There is a limit to how far we can see. Because the universe has a finite age, approximately 13.8 billion years, and because light travels at a finite speed, there is a maximum distance from which light has had time to reach us. This boundary defines the observable universe. Its radius is not 13.8 billion light-years, as one might assume because space itself has expanded during that time. The observable universe is about 46 billion light-years in radius. 46 billion light-years. That number pushes human cognition beyond its breaking point. It is not simply large, it is structurally incomprehensible. Yet it represents the boundary of what we can ever observe, constrained by the speed of light and the age of the cosmos. Everything we know about galaxies, stars, black holes, and cosmic evolution comes to us encoded in light that has traveled across these distances. Light years are the measuring sticks of reality at its largest scale. They are also reminders of limitation. No signal from beyond the observable universe can ever reach us. No information can travel faster than light. The speed limit of reality ensures that some regions of the cosmos are forever causally disconnected from us. In daily life, distance is a matter of inconvenience. In cosmic life, distance is destiny. The concept of a light year forces us to confront the fact that the universe is not only vast but temporally layered. Every glance into the sky is a glimpse into the past. Every telescope is a time machine constrained by a universal speed limit. And in the quiet between stars, across trillions upon trillions of miles, light continues its journey, indifferent to whether any mind can truly comprehend the scale of its path. When you step outside on a clear night in rural America, far from city lights, under a sky sharp with winter air, you are not just looking outward, you are looking backward. Every star above you is a delayed message. The nearest star beyond our sun, Proxima Centauri, is a little over 4 light-years away. The photons touching your retina tonight left that star during a different presidency, under a different global climate, in a world subtly different from the one you inhabit now. That delay is modest by cosmic standards, but it already stretches the intuitive link between seeing and immediacy. In everyday life, sight feels instantaneous. You flip on a lamp and the room brightens without perceptible lag. You glance across a highway and judge the motion of a passing car in real time. Evolution trained your nervous system to assume that what you see is what is happening now. Astronomy breaks that assumption. Light has a finite speed. It may be the fastest thing in the universe, but it is not infinite. Because of that, the sky is not a portrait of the present. It is a layered archive of the past. The moon is about 1.3 light seconds away. When you see its craters, you see them as they were slightly more than a second ago. The sun is about 8 light minutes away. If the sun were to vanish, a purely hypothetical scenario, Earth would continue orbiting the empty location for 8 minutes before gravity's change, which also propagates at light speed according to general relativity, reached us. We would continue to see sunlight for those same 8 minutes. This delay scales relentlessly. Jupiter is roughly 40 light minutes away at opposition. Saturn is more than an hour. Neptune is about 4 light hours from Earth. By the time you reach the outer edge of the solar system, you are already dealing with lags that span human activities, meetings, meals, flights. But these are still local scales. They remain inside a cosmic neighborhood where delay feels inconvenient rather than transformative. The transformation begins beyond the solar system. Consider a star 1,000 light-years away. When its light began traveling toward Earth, the year was roughly the early Middle Ages. Empires were rising and falling. Languages were evolving. Entire civilizations have come and gone in the time it took that light to cross the gulf between us. Now consider a star 10,000 light-years away, on the far side of the Milky Way's disk. Its light began traveling toward Earth before recorded human history, before agriculture, before cities, before writing. And when we turn powerful telescopes toward distant galaxies millions or billions of light-years away, we are no longer peering into human history at all. We are observing epochs when Earth did not exist, when the sun had not yet ignited, when the Milky Way itself was still assembling from smaller protogalactic fragments. This is not poetic exaggeration. It is the operational reality of observational astronomy. Light years do not simply measure space, they measure delay. The deeper implication is that the universe does not have a single now. The concept of simultaneity, already complicated by special relativity, becomes meaningless on interstellar and intergalactic scales. What is happening right now in a galaxy 10 million light-years away is inaccessible to us for 10 million years. We are permanently out of sync with the broader cosmos. This temporal layering turns the universe into a kind of natural time machine. When astronomers study distant galaxies, they are reconstructing cosmic history not from fossils in rock, but from photons in motion. Each increase in distance corresponds to an earlier chapter of the universe's story. Nearby galaxies reveal mature stellar populations, structured spiral arms, settled dynamics. More distant galaxies appear younger, more chaotic, often smaller and less chemically enriched. At extreme distances, billions of light-years, we see galaxies as they were not long after the Big Bang. Their light has been stretched or redshifted by the expansion of space itself. This redshift is not merely a Doppler effect caused by motion through space. It is a consequence of space-time expanding, stretching the wavelength of light as it travels. The concept of redshift allows astronomers to translate light into time. By measuring how much a galaxy's light has been shifted toward longer wavelengths, scientists can estimate how far it has traveled and therefore how long ago it was emitted. In this way, light years become tools for reconstructing cosmic evolution. The cosmic microwave background radiation, the afterglow of the Big Bang, comes from a time about 380,000 years after the universe began. The light we detect from this radiation has been traveling for 13.8 billion years. It represents the earliest moment we can observe directly, when the universe cooled enough for atoms to form and photons to move freely without constant scattering. Beyond that boundary lies an earlier epoch that remains opaque to direct observation. We infer its properties through theory and indirect evidence, but we cannot see it in the traditional sense because light itself could not yet travel freely. Thus, the light year defines not only distance but epistemology. It sets the boundary of knowledge. The speed of light limits how much of the universe we can access. Because the universe has a finite age, there are regions so distant that their light has not yet had time to reach us. Even if those regions contain galaxies, stars, or entire cosmic structures, they remain permanently outside our observable horizon. This horizon is not a wall in space, it is a boundary in time. Due to cosmic expansion, the radius of the observable universe is about 46 billion light-years, even though the universe is 13.8 billion years old. This apparent paradox arises because space itself has been stretching while light travels. The galaxies whose light we now see as extremely distant were much closer when that light was emitted. To grasp this requires abandoning intuitive geometry. In everyday experience, distance is static. A road does not lengthen while you drive it. But on cosmic scales, space-time is dynamic. The metric that defines distance changes as the universe evolves. A photon emitted billions of years ago has been riding the expansion of space, its wavelength stretched, its path extended. The light year, therefore, is not always a simple ruler. It is embedded in an expanding framework. For the human brain, which evolved in a stable gravitational field on a planet with negligible space-time curvature, this dynamic geometry is deeply counterintuitive. Our minds prefer fixed backgrounds and consistent scales. The cosmos offers neither, and yet, this time-delay nature of light provides a profound opportunity. When astronomers map galaxies at different distances, they are effectively mapping different epochs simultaneously. Nearby galaxies represent the relatively recent universe. More distant galaxies represent earlier stages. By comparing them, scientists can reconstruct how galaxies grow, how star formation rates change, how heavy elements accumulate, and how large-scale structure evolves. It is as if the universe has laid out its entire history across distance, inviting careful observers to piece it together. The light year is the stitching between space and time in this cosmic tapestry. But there is a psychological consequence to this realization. When you look at a star 1,000 light-years away, you cannot know whether it still exists in the same state. It may have exploded as a supernova centuries ago, and its light simply has not yet reached us. In a very real sense, parts of the night sky may already be gone even as we see them shining. This is not speculation. Massive stars live short, violent lives. Some of the bright blue giants visible in our galaxy will eventually detonate in supernova explosions. When they do, the event will not become visible on Earth until the light arrives, potentially centuries or millennia after the explosion occurred. Thus, astronomy is an exercise in delayed awareness. The night sky is filled with objects in various stages of existence, but we encounter them only through the lens of time. We never see the universe as it is in totality. We see it as a mosaic of moments, each delayed by a different interval. This temporal fragmentation reshapes our concept of presence. On Earth, presence implies simultaneity. If two people stand across a room from one another, they share the same moment. On cosmic scales, simultaneity dissolves. Two observers separated by thousands of light-years inhabit different slices of each other's history. Special relativity formalizes this intuition. According to Einstein's theory, simultaneity is relative. Events that appear simultaneous to one observer may not be simultaneous to another moving at a different velocity. At high speeds or across vast distances, the idea of a universal no breaks down entirely. Light years expose this breakdown in dramatic fashion. The sky above the continental United States on a given night is not a unified present. It is a patchwork of different eras. Some stars are seen as they were decades ago, others as they were centuries ago. Distant galaxies appear as they were millions or billions of years ago. You are surrounded by delayed messages. This realization does not diminish the sky. It deepens it. The stars are not static decorations. They are active transmissions, each photon a traveler crossing unimaginable distances to deliver evidence of its origin. In this sense, astronomy is forensic science on a cosmic scale. Telescopes do not simply magnify. They collect ancient light. Large observatories in Arizona, Hawaii, and orbiting above Earth are not windows in the ordinary sense. They are receivers tuned to whispers from the past. The larger the telescope, the further back it can see. By capturing faint light from extremely distant galaxies, astronomers push closer to the beginning of cosmic time. Each incremental improvement in sensitivity extends our temporal reach. And yet, no matter how advanced our instruments become, the speed of light remains an unbreakable constraint. We can never observe an event before its light arrives. We can never see beyond the observable horizon. The light year marks the edge of possible knowledge. For the human brain, this is both humbling and destabilizing. We are accustomed to mastery through proximity. We study objects by approaching them, by manipulating them, by observing them in real time. The cosmos denies that privilege. It forces us to interpret echoes. It compels us to build theories from delayed signals. And yet, within those constraints, we have constructed an astonishingly detailed narrative of cosmic history. From the formation of the first atoms to the ignition of the first stars, from the assembly of galaxies to the birth of our solar system, this story is written in light years. Each chapter corresponds to a different depth of space, a different epoch encoded in photons. The distance that breaks the human brain is also the bridge that connects us to the universe's origin. Without light's finite speed, we would see only the present surface of the cosmos. There would be no layered history in the sky. There would be no direct evidence of the early universe. The delay that complicates our intuition is precisely what enables our understanding. The light year, then, is not merely a unit of measurement. It is the architecture of cosmic memory. Across the American landscape, from the deserts of Nevada to the forests of Maine, from the mountains of Colorado to the shores of California, the same ancient light falls each night. It carries with it stories older than our species, older than our planet, older than our sun. And in learning to interpret those stories, we confront the limits of our perception and the vastness of a universe whose scale resists comprehension, but invites relentless inquiry.